This lecture will cover a method called analysis of variance, or ANOVA for short. An analysis of variance is a formal method to both define and quantify the different sources of variances that make up all the variability in your data. And we'll apply this method first to our problem of linear regression. So as you recall, we had an example paired data set of radiometric ages from samples of 4 Hawaiian volcanoes, and the other data that we measured was the distance of each volcano from Kilauea. And so we described each radiometric age, which we called y sub I, as being caused by a linear age distance relationship because of the Pacific plate motion over the Hawaiian hotspot. And in addition, there was some dispersion or variance about that line trend due to other factors. We called that noise, and that noise could encompass, for example, local eruptive histories of the individual volcanoes. It's the other part that's not explained by the linear trend. And mathematically, we described the linear trend as a true intercept and true slope for age versus distance. And then the noise was described by the vector epsilon. And we fit our data, or we approximated the linear trend by fitting our data to a line. And our model fit had the slope A1 and intercept A2. The solutions of which are given here. And just a little more background. So A1 can be described as the difference between the mean value of y minus the slope times the mean value of x. And I'm changing notations here. I'm going back to using the bar as describing the mean. Instead of the caret, which was in another video. And if we substitute this for our intercept, we can describe the model age as being equal to the mean value of y plus the slope times the difference between the position and the mean value of x. Okay, so that's a little background. And here, okay, so ANOVA is an analysis of these different sources of variances. And we have these two sources of variance, the line trend and then the variation about the line trend. And here we're going to use ANOVA to do yet another test of significance of the slope. And this test will be an F test, where F is the variance due to the regression or the variance associated with the line trend over the sum of square errors. Or our sum of square misfits from our line regression. And then the other topic I will cover is so I'm going to define some quantities that are widely used in the literature, especially the R2 parameter. And I'm going to relate that to the slope and the linear correlation coefficient, little r. Okay, so you'll see, you may have already, or you will see R2 referred to in the future, and I'd just like to cover what that is. Oops, but before I do continue, I'd like to correct a couple of mistakes I'm noticing here. The terms in the numerator for the slope, solution for slope, should not be squared. And just to clarify, this product of the deviation of each value of x from its mean times the value of value of y from its mean should be evaluated within the sum. So the product is taken and that product is summed over all values of x and y. Okay, now let's continue on our discussion of r squared. So let's look at the total variance of y, our age data. So the total variance is proportional to the sum over all our data points of the deviation of y from its mean squared. Right, so we would take that and divide by n minus 1 and we would get the total variance. And let's break that into two parts. So we'll have we have a model minus the mean plus each data point minus the model value at each point. Okay, so we've just simply added this model function into our equation for our total variance. Because, as you can see, we're now describing the total variance as a part due to a deviation of the regression from the mean plus a deviation of each data point from the regression. So let's expand that out. So let's carry out a little bit of algebra, and we can write that as the sum over all of I going from 1 to n, of our deviations of our regression from our mean squared, plus the sum over all I of each data point from our regression squared, plus our cross term, which is 2 times the sum over all I of our model values minus the mean times yi minus the model values. And it turns out that if we use if we remember these definitions or this function for our model value, we can substitute it into this and we can show that the cross terms actually go to 0. And you can refer to the Draper and Smith handout, which is posted online. So you can see that we've successfully separated the sum of square total deviations as a part due to the regression, which we'll refer to as the sum of square deviations due to regression, plus the part due to our error or our misfit, which we'll refer to as our sum of square errors. And just to remind you, our sum of square errors is the same thing as what we called big E, which was our error vector transposed times itself. So these are the same thing. And let's look at our degrees of freedom for each of these variances, or each of these terms. So the total number of degrees of freedom is n minus 1, right? This depends on n values of y minus 1 estimate for the mean value of y. The degrees of freedom for our errors is n minus 2, because again we have n values of y, and we have two model parameters, a1 and a2, that we've estimated. And turns out that the sum of the degrees of freedoms for each of these parts must also equal the total, and it turns out that degrees of freedom here is 1. And one way to think about that is from our equation for our model value. The deviation of our model value from y is a function of one parameter of the deviation of our each x value from its mean. So if we look back at our diagram, so here we have our data points, and the black line shows the least squares regression, with the dots showing the values of each regression at each value of x. So the vertical dashed line shows where x bar is, and the horizontal dash bar shows where the mean value of y is. So the difference between each black dot and the horizontal bar describes the deviation of the model from its mean, from the mean value of y. And the difference between each data value and the dot describes the difference between, or the deviation of, the data from the model. And so we can make a table, our formal ANOVA table, that organizes this information. So we have our first column being the source of variance, the second column being the sum of squares for that source, for each source. We have our degrees of freedom, which we also called nu, and then we have our mean sum of squares, and then we have a column for f. And so at the very bottom is the total variance, and that's written as SST, and again was the sum of each of our data points minus the mean value of y squared. The degrees of freedom were n minus 1, and the mean sum of squares is just SST divided by the number of degrees of freedom. Okay, we had the part due to our regression. and the sum of squares was SSR, and that again is the sum of how our model deviated from the mean squared, and that's all summed for all model values. The degrees of freedom were n minus 2. Sorry, not n minus 2, 1. And the mean is MSR, which is SSR divided by the degrees of freedom, which is just 1. And then our other source of variance is the variance about the regression. And that was SSE, and that again was the sum of square deviation of each data point from the regression. And that had degrees of freedom of n minus 2, and the mean sum of squares is equal to SSE divided by n minus 2. And finally, for the F column, we'll take the ratio of MSR over MSE, and that's the statistic we'll use for our test. And you should recall that the F statistic is a ratio of two chi-squared random variables. Or random variables that have chi-squared distributions. So to test whether the slope is significant, we could formulate a null hypothesis that the slope is equal to 0. And the test statistic is F, which again is the ratio of variance due to regression over the ratio or over the variance due to misfit or deviation from about the regression. So let's go ahead and perform this test for our data set, our example data set here. And so I've already have my data loaded into MATLAB, and I've already performed my fit. So let's look at this. And so I have my misfit vector as am minus y, where m is the solution vector for the slope and intercept. The sum of square misfits is E, okay, and big E, which is E transpose E, and that's the same again as SSE. And the sum of square variance or deviation due to the regression is the regression minus the mean y, and that's squared, and that's summed. And then we have our total. And here I calculate the mean sum of square due to regression, the mean sum of square due to about the regression, and then F. And I'm going to compute the cumulative probability of F with the degrees of freedom of 1, so that's the numerator degrees of freedom, and n minus 2, which is the number of degrees of freedom associated with the misfit. And let's go ahead and run this. So I find that my value of f is 5.3, and it has a p-value of 95.3%, or we're in the far right-hand tail of the f distribution. So 1 minus p is just under 5%, or about 4.7% here. And so if I were to have a significance level of 5%, then my value of f is greater than the 5% value of f, so I would have to reject the null hypothesis that the true trend has zero slope. And I've also compared this with our other test, which is using our Pearson's linear correlation coefficient, which I've calculated here. And remember, this was a t-test with t defined like this, right? And the probability value of that t for n minus 2 degrees of freedom, the cumulative probability value is about 97.6%, which puts us in the far right tail of the t distribution. And if 1 minus p is 2.3%. So for this t-test, so our f-test was a one-tailed test, and with a significance level of 5%, we would reject the null hypothesis. The t-test is a two-tailed test, so we have to take 5 divided by 2, or 2.5%, and you can see that our p-value is, or our 1 minus p is less than 2.5%, also consistent with a result of rejecting the null hypothesis. And it turns out that 1 minus p for the t distribution is exactly half of 1 minus p for the f-test. So the f-test and t-test are essentially, well, they're giving consistent results, and they're essentially the same test. So I've just shown you how to use ANOVA for linear regression to test for significance of slope. Now let's go to the second goal to define what R2 is and how it relates to slope, as well as the correlation coefficient. So R2, R squared, is another important ratio, which is the sum of square residual due to regression divided by the total sum of square residual, or total sum of square variance. And this gives the fraction of the total variance due to the regression. Right, so if there were no true trend, R squared would be 0, and that would mean that your data would have a total variance, for example, about a slope, about the mean value of y without any slope to it. Right, all the variances, the total variance is just about y bar. In the other extreme, when R squared is equal to 1, that would describe all the variance being completely due to a linear trend. So that means your data lines up perfectly along the line. There's absolutely no deviation from the line in this case. And I'm just noticing that I wrote the wrong symbol for the mean of y here. So let me correct that here. Right, this is the sum of square deviation, sum of squares associated with a regression. So we want to take the sum of square deviations of the model from the mean. And the mean, of course, is y with a bar over it. So let's write out r squared. Again, it's the sum of square deviation of the model from y bar all over the sum of square deviation of each point from y bar. And we recall that the model is equal to y bar plus a2 times the deviation of each x value from its mean. And if we substitute this equation for the model, we find out that we get that r squared is equal to the slope squared times a factor, which is the square deviation of each value of x from its mean all over the square deviation of each y value from its mean. So it turns out that r squared is the square of the slope scaled by the variance of x over the variance of y. So there's a relationship between r squared and the square of the slope. So now let's look at our correlation coefficient. Recall that r was equal to the covariance of x and y divided by the standard deviation of x times the standard deviation of y. And if we recall our solution for A2, and we square it, so this is A2 squared, and if we substitute that into r squared, we see that r squared is equal to our Pearson's correlation coefficient squared. Or in other words, the square root of R2, we can call that big R, is simply equal to the absolute value of Pearson's correlation coefficient. So in our example of the radiometric ages of our volcanoes, I computed R squared, again as SSR divided by SST, and then the correlation coefficient, which I actually computed above the way we learned it, but also I took the square root of R2. And so R2, R2 is 0.37, meaning that 37% of the total variance is caused by the linear regression. So this line takes up 30% of the total variance of our data points. And the square root of that gives the absolute value of our linear correlation coefficient, which in this case was about 0.61. So that, I think I'm going to go ahead and wrap up here. This is wrapping up the analysis of variance applied to linear regression.